Today we're on page 6 of the chapter 13-14 Chemistry 1 packet, and we're talking about Graham's law of effusion and diffusion. So let's first understand the difference between these two words. If you were to take a balloon and fill it up with air, and the balloon developed a small hole, the air would effuse out of the balloon. So effusion means that a gas is coming out of a small opening. But then after that, it would diffuse throughout the room, meaning it would spread out. So slightly different meanings. Effusion means coming out of a small opening for a gas, and diffusion means it's spreading out in a large area. So if you were to take a look at this box in this diagram, here there's a gas on the left side, there's a partition right here. If you just simply slide out this partition, the gas would diffuse throughout the entire box. But if the partition had a small hole, the gas would effuse through the hole and then diffuse throughout the entire section. Now what we want to do is we want to compare how fast gases will effuse out of a hole or diffuse throughout a region. And in order to understand that, we're going to have to take a look at a quick story. So here is a truck, and we're going to contrast that with a car. Some sort of sports car. And both of these vehicles want to knock over a wall. And these figures are not drawn to scale. Okay, so the truck, which is big and heavy, versus a much lighter sports car, the truck only needs to move at a certain low speed in order to knock over the wall, but the car would have to travel at a faster speed to knock over the wall to have enough energy to knock it over. So in physics, and chemistry actually, kinetic energy is related to 1/2 mv squared, where m is mass and v is velocity. So these vehicles have to have the same kinetic energy of motion, to knock over the wall. Okay, so you need the same amount of kinetic energy to knock over both these walls, but since the truck has a large mass, it only has to have a small velocity. But the car has a much smaller mass, so it has to have a higher velocity. So since both of these have to equal each other to knock over the wall, we could set them equal to each other. So 1/2 mv squared of the truck equals 1/2 mv squared of the car. So we'll call this 1, call this 2. So we could just multiply by 2 on each side. The 1/2s are going to drop out. Then we're going to get all the velocities on the left side. So it would be v1 squared over v2 squared by dividing each side by v2. And then let's get all the masses on the right side. So the m2 is already over here. We're going to divide the m1 into that side. And then to get rid of the squares, we're going to square root both sides. So what you're going to have is v1 over v2 equals the square root of mass 2 over mass 1. Okay, so if we call number 1 the truck and number 2 the car, what we're saying is that the velocity of the truck divided by the velocity of the car will equal the square root of the mass of the car over the mass of the truck. And that is Graham's law right here, where rate is like velocity. So if you have two gases and you want to figure out which gas is faster, the lighter gas is going to be faster than the heavier gas, and the ratio is going to equal the square root ratio of the opposite order. So this is a square root sign if you want to add in this. I couldn't do that on the computer before. All right, so let's take a quick look at this. Let's take the ratio of carbon dioxide and helium. So you know carbon dioxide is CO2, and that weighs 44 grams per mole. And you know that helium is a much lighter gas weighing only 4 grams per mole. So since the question is asking for a rate of carbon dioxide to helium, we're going to do that order. So we're going to say the rate of CO2 divided by the rate of helium equals the square root of their molar masses opposite order. So here's 4, here's 44, and if you take that ratio, you're going to find out that it comes out to be 1 over 3.3, which is 0.303. So what does that mean? Since it came out to be less than 1, that means that CO2 is slower than helium. So you would say CO2 is 0.303 times as fast as helium. Now, if you want to go the opposite way, it'll be a little easier to understand. So let's contrast it with doing it the opposite. Put the helium rate over the rate of CO2. Then when you square root their masses, up here is your 44, up here is your 4. And when you do that, you get 3.3 to 1. So that means that helium, excuse me, is 3.3 times faster than, having some difficulty here, right now, than CO2. Okay, let's move on to the bottom of the sheet and contrast time. When we're talking about time, it's not going to be the same as the rate ratio, because if you are a faster gas, you're going to have a lower time. So here you'll see that we're not switching the 1s and the 2s. They're staying the same. So if you want to contrast helium and carbon dioxide, this is what we're going to see. So when we do time, we could put time of helium compared to time of CO2, square root of their masses, but now we don't switch their masses. So this is going to be the molar mass of helium over the molar mass of CO2. So it took 20 minutes for helium to effuse. So I'm going to write 20 minutes right here. And then I don't know the time it took the CO2. Of course, I do know their molar masses. So helium weighs 4, and carbon dioxide weighs 44, square root. Do your math for this, and you get X to be 4,400 minutes. So let's think about this. Does it make sense that helium takes a short time, 20 minutes, and CO2 takes a long time, 44 minutes? Yes, it does, because CO2 is very heavy compared to helium, so it's going to take a longer time to effuse out of the hole.